Okay. Where did we leave off last time? Let's see here. Talked about absolute values, correct? We moved on to the year principle. Let's see here, my notes are jumbled up here. Move back in time here. My notes are all out of order here. 4, 5, 6, 7, now they're in order. Okay. And so last time we were just talking about the EAR principle. What does EAR stand for? Evaluate, approximate, and render. Yes. Okay. Are we still on section 1.3?
We were about to finish.
We're about to finish it. Okay, so what part of 1.3 do we have left is what I'm trying to. I feel like we didn't have anything left, right? Did we do examples with absolute values? We did? Okay, let's just do one more example. And then we'll move on to 1.4. Because I think we are done with 1.3. One more example in 1.3, 1.4. So example, let's approximate this. Okay. What does this equal? Should I put a minus here or leave it a plus? Why? Yeah, so that -5 wins. So the absolute value puts a negative there. So we get +5 minus omega minus 5. So what happens here? Approximate the numerator and the denominator, right? So what happens when you get that? Well, we can just say that this is it. But we could also render a real result as well. What could we say that renders the real result? We can also say it renders the real result 0. It depends on what you're looking for and what it's asking. Technically, you can render the real result 0. Why is that? Because the what?
Answer is too small, like the closest number gets is 0.
Because the numerator is very small, right?
Yeah.
Yeah. So the overall fraction becomes very small. Okay. Moving on to 1.4. Here we talk about limits. This is a central concept in calculus. It is actually the central concept in calculus is the limits. It is the most important concept in the study of calculus. It's what makes calculus calculus. It is the addition to the knowledge that wasn't there before. It is the concept of the limit. And it's a solution to getting around the dividing by 0 problem. Let's say on a function like this. Okay. We want to know what is f of 3. So we evaluate the function. And then this gives me what? Right? So what is f of 3? It's undefined. And we know why you can't divide by 0. We've shown it. And we know why 0 over 0 doesn't equal something like 1. We show that when 0 is in the denominator, a very special phenomenon occurs that doesn't occur for any other number. So f of 3 doesn't exist, right? It doesn't. Why is it that we can graph this function? And it looks like f of 3 exists and it equals 8. Huh?
That's something infinitesimal?
Because something infinitesimal?
Yeah. That's infinitesimal. I don't know.
Huh?
I'm just guessing.
That's fine. That's wonderful that you're guessing. There's nothing wrong with that. This is how you learn. You guess and you get it checked, right? Because I'm here, I do that for you. In the future, when you become a mathematician, you will do it for you. You will get the tools in order to go quantify the veracity of your inquiries. Means go check to see if you're right. I'm fancy schmancy way. Well, notice we can't put 3 here for x. But why don't we use this young man's idea and use something that's close to 3 but not 3? Like what? Yeah, 3 plus an infinitesimal. You can use little omega, you can use alpha, it doesn't matter. Okay. We use alpha for now, just to be truly arbitrary. Let's see what happens when we do that. We get 9 plus 6 alpha plus alpha squared plus 2 alpha plus 6 minus 15. Everything divided by just your alpha. All right, so then let's combine like terms, shall we? We got alpha squared plus 8 alpha. 6 plus 9 is 15, so minus 15 is 0. All over alpha. All we can do is factor out an alpha. Cancel out the alphas, and we get alpha plus 8. But we can approximate this to what? Approximately 8. You could even say that it renders the real result 8. Okay. So that's why this is happening. It seems like the function isn't defined at 8, but it is defined a little bit to the left, infinitely to the left, and infinitely to the right, but not at 8. Typically for functions like that, we put a hole in the function. I didn't put the hole there initially so that you guys wouldn't know that it was there. I wanted you guys to discover that it was there. because you only see that hole if you zoom in really far into the graph. This is the power behind calculus. It allows you to almost divide by zero, to basically divide by zero. For all intents and purposes, we just divided by zero. Because for all intents and purposes, this is basically zero. If this is alpha, it's basically zero. But notice we allowed the algebraic consequences of canceling out this minute quantity with the minute quantity above to allow us to extract a finite value, not an infinite value, because usually if you divide by something near zero, your overall fraction becomes what? Your overall fraction becomes what when you divide nearly by zero?
Can you say that again?
It becomes infinite.
So nearly zero, it becomes infinite, but if it was zero, that becomes undefined.
Absolutely right, young man.
Okay.
Absolutely right. Absolutely right. That proof I showed you where dividing by zero leads to contradictions was when you divided by the actual number zero. Now we're dividing by an infinitesimal, which is technically not zero by definition. Infinitesimals are not zero. We can approximate them to be zero with infinite precision, but they're not zero. We're getting to have our cake and eat it too here. And that's why it was such a revolutionary discovery, because it allowed us to evaluate functions at these very tricky points, all the while not doing anything logically inconsistent with all of mathematics. So let's define this concept of a limit, this very useful concept. Okay. Let f be a function, be a real number, if f of b plus alpha is defined and renders a real result, i.e. not something like plus or minus infinity, right? Remember I told you how we can include plus or minus infinity as the extended real numbers? Well, we're not working with the extended real numbers. We're just working with the real numbers where plus and minus infinity aren't numbers. You can construct a number system in which plus or minus infinity do become part of your number system. And they would behave very much like capital omega. But we're not doing that here. What we want to do is have a different way of thinking about it. We want to say, okay, here's the reals. We don't want to add plus infinity and minus infinity over here. We just want to say all of the reals, even towards the infinity, is just one little piece of these capital omegas. And so that's how we want to deal with it. When you invent new mathematics, it's up to you how you want to create it. It's like painting a picture. You can decide to start with the color red. You could decide to start with the color blue. It's up to you. That's what mathematics is, really like an art form. And that's what people don't get. Mathematics is truly like an art form that utilizes critical thinking as well as creativity. So let's say that the real result it renders is equal to L, i.e. this is what your f of b plus alpha is. And and alpha is any arbitrary infinitesimal. I don't have to say that anymore. We all know that. Then this implies that, are we defining it? Yes. The limit, LIM is short for limit, as x approaches b of f of x is equal to L. Okay? And what we end up saying is this is also equal to evaluating the function at b plus some arbitrary infinitesimal. So this is very important right here. And it teaches you how to take a limit for as x approaches some real number of function. We say that it equals L, the limit value. L is the limit value, a real number. And it's equivalent to plugging in a b plus alpha in for x in your function, like we did earlier. Remember? We calculated the limit as x approaches 3 earlier of this function. What was it? Plus 2x minus 15 over x minus 3. We calculated the limit because we plugged in a 3 plus alpha, remember? And that equals 8. It rendered the real result 8. So the limit as x approaches 3 of x squared plus 2x minus 15 divided by x minus 3 equaled 8. And 8 is this limiting value. Notice when we plugged in a 3, we got an undefined. It allows us to get away with nearly dividing by 0, which is incredible. Because now we can extract meaningful information out of those functions even near those regions. You may not think that that's such a big deal, but if you go back in history and you're mathematicians who have been confused for hundreds of years or didn't know how to do this or thought it was previously impossible, and someone pulls off something that was thought to be impossible, you would be impressed, right? Yeah. It's like, who thinks jumping up in the air and spinning 10 times before landing on your feet, 10 times backflip is possible for a human being with no trampoline or no assistance? 10 times. Who thinks it's possible? No one thinks that's possible, right? 10 flips. That's really hard. But if someone just popped up and did it, you'd be impressed, right? Yeah. So that's kind of like what's actually happening here. That's exactly what's happening here. Mathematically, someone did that. Now we're studying the consequences of this new technique that allows us to do this. Okay? So, in an abstract sense, let's say you have some like arbitrary function. Here's your b. If the limiting value exists, here's your L. Here's your b comma L. And this is your f of x. That's when the limit exists. If the limit does not exist at b, you'd get something like this. A hole there. This is when the limit actually equals what you evaluate the function. And we've had situations where when we evaluate the function, it equals exactly what the limit is. So like if somehow f of 3 here also equaled 8, if it did, but it doesn't. But if it did, this is what you get. Because it doesn't, this is what you get. Okay. Okay. I'm gonna leave this here because it's very important. So let's practice our limit taking abilities. Let's take the limit of this function. Okay? The limit as x approaches 1 of this function is tantamount to saying take, here's our f of x, right? It's saying take f of 1 plus some arbitrary infinitesimal. Something close to 1, but not at 1. Why do we choose alpha but not omega? Because alpha's sign is arbitrary. It could be a positive number, it could be a negative number. So it could scoot to the left of 1 if it's negative, or to the right of 1 if it's positive. So we keep it arbitrary, so it dances around possibly. So if we replace every x with a 1 plus alpha, here's what we get. Right? So then that implies we can factor out alpha from the numerator, allowing this to cancel, which gives us an alpha plus 2. Notice that this approximates or renders the real result. What? But notice, if we were to just plug in f of 1 into the function, which plugging in 1 plus alpha is basically like plugging in 1. Notice what happens. Again, being able to solve this problem was like someone jumping up in the air and doing 10 flips at once and landing on their feet perfectly. In an intellectual sense. That is a physical achievement. This was an intellectual achievement. So in terms of an intellectual achievement, to get around this problem was astonishing. And it required imagination. It required imagination to think about smaller numbers and the extent of numbers and how big can a number get, and how tiny can a number get, and how can we use very tiny numbers that are basically 0 but not 0 to get around this problem. It's incredible. All of the computers you guys use physics. And physics was invented off of the backbone of calculus. Okay, let's keep practicing our limit-taking abilities.
So then on that, the limit is 2.
Yes. Yes.
And the x would be 1, right? Carry f of x.
Yes. Yes. You're saying the limit is 2.
Yeah.
This is the output of the function on the y. The input of the function is alpha plus 2. So the value would exist at alpha plus, I said alpha plus 2, I meant alpha plus 1, comma 2. This is where it would be, here's 1, and right here at 1 is alpha plus 1. They're like at the same point for all intents and purposes. Then over here, there's 2. Your function would exist at this value, at alpha plus 1. But if you move to alpha or to just 1, it becomes a whole. Because then you're dividing by 0. Why is this happening? Who here has heard of the terminology of a singularity? Who's heard of the term singularity? Nobody's heard of a singularity in here?
I remember the word, but I don't know.
Where did you hear the word?
To be honest, I think I heard it on a cartoon.
You heard it in a cartoon?
Yeah.
That's okay. Cartoons are cool. I like cartoons too. Like Dragon Ball Z. Kamehameha! Yeah, that stuff was cool. It's okay to hear a word in a cartoon. Although I don't think Goku ever talked about singularities.
No, I don't think so.
No. Okay. So the reason, who here has heard of black holes? Everybody heard of black holes? What do you guys think black holes are? They're nothing. Okay. Where do you think black holes exist?
Everywhere.
They exist everywhere. Is there a black hole right here?
No. And like in talking in dimensions, it could be. Like
You're not wrong.
it's a deeper thing.
No, yeah, not wrong. Yeah, there could be a microscopic black hole in front of us. There could be microscopic black holes coming in and out of existence. This is actually true. It's by the Heisenberg uncertainty principle. It states that momentum and position must be greater than or equal to h bar, but virtual particles violate the Heisenberg uncertainty principle. And so virtual particles could actually have infinite momentum. And if two particles of infinite momentum colliding could create a virtual black hole. But it's a virtual black hole, it's not a real black hole. Now, if we were going at nearly the speed of light, the virtual particles in the vacuum model real particles. They become real particles based off of the Lorentz contractions. So this is called the Unruh effect. The point was talking about a singularity. A singularity is a region of space and time in which gravity is deciding to divide by 0. Who here knows what density is defined as? Anybody? Mass over volume, density. That's right. A black hole forms when a star explodes and its core implodes. So this ends up becoming an infinite value because the volume shrinks very small. The volume becomes infinitesimal compared to the mass. So understanding about these regions where we're dividing by 0 will allow us to understand more about black holes, which have to be the most interesting objects in our universe. The most interesting. You guys think black holes exist? You think they exist? You think they exist? Well, I thought you said they're made out of nothing. Can something that's made out of nothing exist?
I guess so.
Or does it exist even though it's made out of nothing because you think about its existence? Now that's a philosophical question right there. Let's practice taking another limit. How about the limit as x approaches 4, x minus 4, over x squared plus x minus 20. Notice what happens when we plug in a 4 right away. What is f of 4? Right? F of 4 is undefined. But if we want to take this limit, this is the same thing as saying okay. Then let's combine like terms here. We got alpha on top, alpha squared, go away. And then 8 plus, there's 8 alpha, yeah, plus the alpha, that's 9 alpha. And then these go away. And then we combine the 16 and the 4 to get a positive 20, and it cancels out with that negative 20. So they just go away. Let's factor out alpha from the denominator. Let's cancel out these alphas to get this. What does that? What does this render the real result as? Why? Yeah, it's insignificant compared to the real number 9. It's an infinitesimal. Notice we extracted the information 1 over 9. Where before it was like no information possible. This is what we need to be able to do with black holes here. If we could do this, we will establish a theory of quantum gravity. Who cares about a theory of quantum gravity? None of you care about a theory of quantum gravity? You don't know what it is, therefore you can't care for it, right? I see. We'll discuss more what a theory of quantum gravity means later on in this class. Even though this class isn't about quantum gravity, the mathematics in which you're learning will allow you to understand that stuff. So that's what's really cool here, is that we're undefined in that way, but defined in this way, and they're basically the same thing. Doing this right here and doing this right here, this whole thing was basically the same thing, but you arrive at different results. That's what's astonishing. Okay? So our limit is 1 over 9 for this function. do another one. Then the problem would have been trivial if I wrote that. All right. Notice what happens when we actually evaluate the function at 2. We're dividing by 0. I don't have to do it. Notice when there's a 2 minus 2 in the denominator, you're dividing by 0. It can't happen. So we're going to have to do this thing where we replace all of the x's with a 2 plus alpha. All right, so let's see what this does. 7 and 2 give me 9 plus an alpha minus a 3. Let's go there. 2's cancel here, so you just get an alpha. Now what? Now what? Is this what you're thinking? Okay, but that gives us what? Right. But can we do that? Why not?
Approximation.
Yes. What is that principle called? This violates the what? What's it called? Yes. It violates the approximation principle. So we can't do it. Why? Because when you violate the approximation principle, what you're doing is not doing anything at all. So we want to do something significant. So everything from here on is can't do it, can't do it, can't do it, can't do it. So let's start back off here. I'm going to rewrite what we have. Recall how we get away with situations like this is we utilize the what? The conjugate operation. Multiply top and bottom by fancy number 1. What is anything divided by itself? Except 0. There we go. You guys were hesitant to say anything. Good, except 0. But, so then that means this is multiplying by 1. Right? This is itself divided by itself. This whole thing is the number 1. This whole thing in this parentheses is equal to the number 1. So what is 1 times anything? Itself, right? 1 times anything is itself. So when we do this operation of multiplying this times that, nothing changes. That's why I can say equals. This y I can say equals because nothing changes. What you have on this side is going to be the same thing as what you have on this side. That's why we can even say it equals, right? Because it really does equal. Over here, when you do the multiplication, you get, when you FOIL, you get this. When you multiply this times this, you get 9 plus alpha. This times this, you get 3 square root of 9 plus alpha. This times this, negative 3 square root of 9 plus alpha, which cancels out the term prior to what I just said. And this time this gives you a negative 9 not the square, just a negative 9. Okay. So then notice that the 9's cancel here. And what you get is a alpha over alpha times the quantity. And then you notice that the alphas cancel here. So that what happens over here is you get 1 over the square root of 9 plus alpha plus your 3. Now let us utilize some approximations here. Right? And this ends up equaling what? When you take the principal square root. Could have said that this renders the real result. So take a look. When you violate the approximation principle, it ended up equaling 0. When you didn't violate the approximation principle, we got it ending up 1 over 6. So notice what I meant by this is a violation of the approximation principle. Don't do it, because when you do it, it's like you're doing nothing at all. This is the something that we were trying to do. Doing nothing at all is this. And that's why that approximation principle is a principle to begin with. It's to prevent you from doing nothing. We're inventing these tools to actually do something with it. And our doing something in this problem was extracting what is the value of this function right here, very close to 0, but not at 0. I mean, very close to 2, but not at 2. That's what I meant to say. Very close to 2, but not at 2. So when you have square roots, you're going to have to utilize this operation here. What is this operation called? All I did was I got this, I got that, and I switched the sign in front of it and multiplied top and bottom by it. What's that called? The conjugate. Don't forget that. That always works with the square roots. There's also a complex conjugate, right? We talked about that last class period. So for this function, we draw out the function. We go to 2. We find out this is at 1/6 that the function over here, when you evaluate it at 2, it's not defined because you're dividing by 0 when you evaluate it at 2. So we put a hole there. But to the left and to the right, it has a value of that 1/6. So we can say, oh, we know the function is coming down like that. How do we know it's like coming at this orientation? Well, we then can evaluate it at 1, and then we can evaluate it at 3, and we realize that it is coming in at that kind of orientation. Let's do another one. This is going to be fun. The limit as x approaches 0 of x sine of 1 over x. What is this? And doing this section might take 2 full class periods, and I don't mind that because this is the most important section of this whole class. knowing how to do all the stuff up to here, and this will allow you to be able to handle the whole class. Make sure you get it and make sure you work hard now and not regret later. Work hard, work really hard right now, okay? So let's try and evaluate this limit. Notice that if we were to just plug in, if this is f of x, what's f of 0? 0 times sine of 1 over 0, which what is it? What is that? That's undefined. How can we take the sine of something undefined? Right? Oh, I know what you're thinking. Oh, but if this is undefined and we multiply it times 0, then it should just equal 0, right? Well, you can't multiply 0 times something undefined. Not in this formalism. One could argue you could. But if we say it's undefined, then yeah. You could create a mathematics where you could say that this should equal 0, but not in this theoretical construct. We say that we can't do this. Okay. So let's try to use the limit idea. The limit as x approaches 0. It's just like evaluating the function f of 0 plus alpha, right? So this becomes a 0 plus alpha sine of 1 over 0 plus alpha. So this just becomes alpha sine of 1 over alpha. This is the same thing as alpha sine capital A, which capital A, if you recall, is defined to be 1 over alpha. Capital A is the arbitrary infinite number. Alpha is the arbitrary infinitesimal. Very similar to how 1 over omega is equal to capital omega. But what is the sign of an infinite number? Again, there's no way of knowing what this equals. We're still in a situation where we're stuck. So what do? We're going to use the transfer principle. So we are out of time, but I will say that this problem gets solved by the transfer principle. And before you guys go, you guys got to tell me, what does the transfer principle say? Before you can leave, you have to tell me, what does the transfer principle state?
All algebraic equations true for all real numbers working of hyperreal.
Aha! So surely we are going to use some type of hyperreal number to get around this problem, right? I'll leave that for Friday. And I will give you an extension on this homework.